Well, thank you for that introduction. I'm a fourth year PhD student going into my fifth year now in the Institute for Computational and Mathematical Engineering at Stanford. My advisor is Gianluca Iacarino. In this talk, I'm going to start by presenting the specific wind farm control problem that I'm looking at and presenting it in a mathematical formulation. Then I'll talk about differentiable predictive control, again in a mathematical sense, and compare the mathematical formulation to that of model predictive control and reinforcement learning. Next, I'll present a learning-enabled wake model, which is necessary to apply these methods. And then I'll present the results from two different test cases. One of them will be a static formulation of this hybrid control problem, and that will actually be applied to wind farm control. And then just because of time constraints, I'll be presenting the dynamic case for building control. And then I'll provide some conclusions and directions for future work. For the control problem that I'm looking at, it's wake steering. The image on the left illustrates wake steering. So these are two different images of a top-down view of a wind farm with two turbines indicated with black lines. The wind is coming from the left-hand side of the image. The top plot shows what the wakes look like in the absence of a control method. So the turbines are just facing directly into the wind. The colors that you see are the wind speed, where yellow is high wind speed, blue is low. And you can see that the second turbine sits directly in the wake of the upstream turbine, leading it to produce less power than it could. In the bottom image, you see that the first turbine is yawed to steer the wake away from that downstream turbine, which allows the downstream turbine to produce more power. This comes with a reduction in power for the upstream turbine because it's yawed and angled away from the wind. So in a mathematical sense, my control problem, which I'm going to call P of big T, is to maximize the power that the farm produces. I'll do this over a series of control time steps, starting with 1 and ending with big T. In this problem, I'll refer to the state as xt, where for the wind problem, the state includes the wind speed and the wind direction at each turbine. I'll refer to exogenous data as wt, where this includes the free stream wind speed and wind direction. And then the control action that I'm trying to find is ut, and that's what the yaw angle should be for each turbine in a wind farm. In a schematic sense, if you solve this control problem just once, what that would look like is you take in your first state x1, your exogenous data w1 through wt, solve your control problem, and then you output the control actions for every single time step. You can then apply those to your system, starting with state 1, apply u1, get your next state x2, and then repeatedly do this to get all of your subsequent states. This control problem relies on having a dynamics model, which here would be our wake model. And that dynamics model takes your state, exogenous data, and control action, and then gives you your next state. And one of the issues with this very general approach to the control problem is that your dynamics model typically has error. So if you solve your control problem using that dynamics over a very large control horizon, then as you repeatedly apply that model, you accumulate error, leading to issues in the control actions that your control problem outputs. Model predictive control is a different model-based approach which tries to address this problem. This central loop here is the same as in the previous problem, except now we're only solving that control problem over a look-ahead horizon h, which is smaller than that control horizon t. You output all of your control actions, but now you only take the first control action, and taking that first control action gives you your next state. You take that next state and repeat the problem. And the goal of doing all of this is to reduce the error that you accumulate from that dynamics model. This approach is very commonly used for dynamic control problems. It does have a shortcoming, which is that depending on the cost of your model of your system, it can be very slow online, which can cause problems for trying to use it for real-time control. Learning-based and model-free approach to get around this issue is reinforcement learning. Online, what that looks like is you take your state xt, your exogenous data wt, just for one time step. You input that to your policy pi theta, where theta are the parameters of the policy. Your policy typically is an analytic function, such as a neural net, and this outputs your control action for that time step. You apply that either to your actual physical system, to your wind farm, or much more commonly, you would apply it to a model of your system to output the next state. And then the system repeats. This is very fast online because all you have to do online is evaluate your policy. The downside of a learning-based approach is that offline you have to train what that policy should be. And for a model-free approach, this can be very slow because you're starting with no information about what your policy should be. So the way that training works is that you take a sample of data, your current state, and then your exogenous data. With some probability PT, you take the control action, which is indicated by your policy. And with some probability 1 minus PT, you take a control action at random, where the goal of taking these random actions is to explore your control space and see if there is an option out there that's better than what your policy is currently predicting or currently telling you to do. You then take that control action, apply it to your system or your model of your system, and that gives you your next state. And then the cost of being in that state and taking that action, or conversely, the reward. In this case, we're talking about a reward, specifically how much power your wind farm produces. You then update your policy to try to decrease your cost or equivalently increase your reward or increase how much power you're producing. And you do this repeatedly to train what this policy should be. Now getting to differentiable predictive control, or DPC, online is the same as reinforcement learning. The difference is in how that policy, pi theta, is learned. And pi theta here we're going to take to be a neural network. So offline during the training phase, you have that same inner block I just showed, where you iterate over your time steps and apply your policy repeatedly. Once you've done this for one batch of training data, you then sum up your costs of all of those state action pairs. So basically you're summing up how much power you produced at every time step. You then take the derivative of that sum of powers with respect to the parameters of your policy. What this means is you're actually differentiating through this whole loop over and over again. So you're differentiating through your wake model. And then you take a gradient descent step to update what your policy parameters should be. And you do this repeatedly to train your model. So to summarize these different control methods, model predictive control is a model-based learning-free approach. It solves an optimization problem online, which can be very slow. There's no offline stage. Reinforcement learning, talking about the model-free version here, is a learning-based method. Online, it's very fast because you just have to evaluate a policy, but offline it can be slow because you're trying to train your policy with no model or no information about what that policy should be. And then DPC, differentiable predictive control, is this hybrid of model-based and learning-based, where in the ideal case, online, it's fast because you're evaluating policy, and offline, it's faster than reinforcement learning, for example, because you're starting with a model with some information about your policy. The main shortcoming of DPC is that it can be hard to implement because you basically have to implement all of the components of a model-based and a learning-based approach. So one of the shortcomings of DPC is that you have to essentially re-implement your model of your system to be in some sort of learning package, such as PyTorch. And you have to do that so that you can do this differentiation through your model and then do a gradient descent step to update what your policy parameters are. So I'm going to start by talking about a static case here, a static wake model, because of kind of just the implementation difficulties. That's where I was starting. So the specific wake model I used was FLORIS, and I started with their Gaussian wake model and velocity deficit. I re-implemented this model in PyTorch. And again, that's to enable differentiation of the model, well, through the model. Kind of want to differentiate through this orange block here to do the gradient descent update step. This is what that PyTorch version of FLORIS looks like for a 2x2 turbine array. This plot on the left is showing it if all of the turbines are facing directly into the wind, where the wind is coming from the left-hand side. And then the plot on the right shows what it looks like if you apply control. So the first two turbines are yod. And these plots match those from FLORIS. I then looked at applying kind of a static form of DPC using this PyTorch implementation of FLORIS. DPC is inherently a dynamic method. So to some extent, applying to a static problem isn't really right use of this nomenclature, but I'm going to stick with static DPC just in the context of this talk. So what this looked like is that online, you have some exogenous data, the free stream wind speed and wind direction. I apply a policy to this, and that outputs the control action. And then that control action is the input to the PyTorch implementation of FLORIS, which then outputs what the cost is of that control action. Really what it outputs is how much power you produce using that control action for the exogenous data. Offline now, I take this online series and then I differentiate the power with respect to the parameters of the policy and then take a gradient descent step. So you can see that even though this is static, there's still a lot of similarities to that DPC method I previously presented. You're still using the policy online and then you're differentiating through the model offline to learn it, which is why I'm referring to it here as static DPC. Here I'm showing some results for actually applying static DPC to this PyTorch implementation of FLORIS. So the training set here is I have a fixed wind direction, and then I take a wind speed drawn uniformly from 0 to 8 meters per second. And I'm again applying that 2x2 turbine test case you previously saw, where the wind is coming from that left-hand side still. I then test on a fixed wind direction, that same wind direction, and then this set of wind speeds, 4, 5, 6, 7, 8 meters per second, the same 2x2 turbine test case. I find that after training, DPC gives the same optimal yaw angle as FLORIS for all of these test cases, where basically it's yawing the first 2 turbines to their maximum, and then the downstream turbines don't get yawed at all. This image on the left shows what the training looks like. The vertical axis is the average power over this test set that I get using my policy with the parameters that have been trained so far. So the horizontal axis then is the training epoch. And you can see that the average power over the test set improves as we keep training those parameter policies. And it levels out up here around 2220, which is the same maximum power that FLORIS predicts for this test case. So this shows that the training is working smoothly. I just wanted to comment the reason why I'm showing the results over the test set rather than over the training set, which is what I actually trained on, is because the wind speed varies a lot in this training set. So if I were to just look at the training results, it would appear very noisy. I don't use my test data during training. I'm just evaluating on it to see how well the training is working. So basically what happens is once you have this trained policy, I could then use that instead of a lookup table, which typically is what gets used with FLORIS. My main goal for doing this static test case was to start building up the capabilities I needed for using DPC for a dynamic test case. I do think that there is some benefit to using the policy, this neural network that comes out of DPC for the static test case. Specifically, I think it has capabilities to do some things that you can't do with a lookup table, or that would be harder to do with a lookup table. For example, if you have a case where some turbines are failing, in order to generate a lookup table that can give accurate control for the cases where some turbines fail, you would have to look at every single permutation of turbines that could potentially fail, and then run your optimization loop to find the optimal control for every single one of those test cases. There's the potential that using a method like differentiable predictive control, you could train it by only looking at a subset of those circumstances, meaning you don't have to have this giant lookup table. You don't have to run as many test cases necessarily. Another benefit of having FLORIS in PyTorch is that it can make learning, for example, parameters or model corrections easier because you already have your wake model in this learning setting. Now I want to move on to talking about differentiable predictive control for a dynamic test case. I don't have results yet for wind farm control, so I just very briefly want to talk about building control to give a sense of what DPC can look like and the kind of benefits you can get by using DPC for a dynamic test case. So for the building control case, we're talking about physical buildings like the ones you see in this image. You can split up those buildings into different zones. And then in building control, what you care about is keeping the temperature in each of these zones comfortable while minimizing the cost to do so by setting, for example, central cooling, and then how much power you send to each fan to distribute that cool air to each of these zones. Jumping to the results, here I'm comparing DPC, MPC, and reinforcement learning for this problem. On the vertical axis of the left plot, you can see how much error there is. For model predictive control, that is a function of the look-ahead horizon. So if you remember back to the start of the talk, I mentioned that for MPC, you're kind of optimizing over this look-ahead horizon, and then you do that repeatedly. Well, the cost of the method depends on how long that look-ahead horizon is, and the error does as well. So for a large look-ahead horizon, you get more accurate results. You can set error coming down. For a very large look-ahead horizon, the accuracy is comparable to that from reinforcement learning or differentiable predictive control. If you look at the plot on the right, though, the online optimization cost is increasing with that look-ahead horizon. So if you want accurate control for model predictive control, online is going to be much slower than reinforcement learning or DPC. Now, comparing DPC and reinforcement learning, for the training time, DPC takes about a quarter as long to train as reinforcement learning. So this shows for a dynamic test case how DPC can kind of hit that sweet spot where it has similar or better error to a model-based method, but a much lower online optimization time, and then similar accuracy or even better accuracy than a learning-based method, but much lower offline training time. Again, the downside of DPC is you basically have to implement all the components of MPC and reinforcement learning. So to summarize, DPC is a hybrid model.
Offline, that's why, sorry, she does the computation offline. That's why it's 0 for DPC.
We can hear you talking, however. Okay, so to conclude, DPC is a hybrid in between a model and learning-based dynamic control method. I presented a PyTorch implementation of FLORIS, which is basically just a learning-enabled version of that model. I showed what DPC can look like in a static wind farm control setting. I get comparable results to a lookup table, which is currently what gets used with FLORIS or other static wake models. However, I expect that it will be more versatile than a lookup table. For example, you could train to consider turbine failure or learn model parameters more easily than with a non-learning enabled version of FLORIS. And then I showed results for dynamic DPC applied to building control. Specifically, I showed that I get similar performance to MPC and reinforcement learning, but I have lower online costs than MPC and lower offline costs than reinforcement learning. The one caveat is it's more involved to implement than either of these methods. In the future, I'm going to continue this work using static DPC with the PyTorch version of FLORIS. I'd like to consider dropping out turbines and see how well it actually works in that case. If there is a benefit over the lookup table approach, consider a larger farm than just this 2x2 turbine case, and also look at varying the turbulence intensity and wind direction, not just wind speed. Then I would like to apply DPC to dynamic wind farm control. I think that'll extend very naturally from this work because I plan to use the dynamic version of FLORIS, Floridyne, which was talked about in one of the earlier talks in this conference series. And then I would like to actually evaluate DPC in LES rather than just evaluating on FLORIS or Floridyne, specifically AMR wind. And finally, there's a project that I'm connected to that's looking at combining wind farm control with solar and storage to provide grid services. So tracking some sort of power signal. And that'll be the ultimate goal, being able to use DPC in that setting. I'm also open to more ideas. If you would like to use the PyTorch version of FLORIS that I've developed, I'd be very happy to share that. And I'm also happy to share the PyTorch version of Floridyne once it's available, hopefully this fall. I'd like to acknowledge my collaborators at the National Renewable Energy Laboratory. For building control, I worked with Dave Biagioni and Zhangyu Zhang. We're working on a paper on that work, which will be out hopefully shortly. And for wind farm control, I'm currently working with Jennifer King. I'd like to acknowledge my funding from Stanford and the Department of Energy. My work cited, and at this